Okay, welcome everyone, and thanks for joining the Manchester Java community today. First off, I should say thanks to our sponsor, RecWorks, who pay for the meetup fees for the Manchester Java community. We really appreciate this, so thanks to them for providing this sponsorship. So today we're joined by Ron Pressler from Oracle, who is the technical lead for Project Loom. Thanks for joining us, Ron.
Thank you.
Today's session is slightly different in that it's a Q&A session. So if anybody joining us today has any questions about Project Loom, please feel free to ask them in the chat area on Zoom today. We'll start off with a few prepared questions, but there is time set aside later to cover any audience generated questions. So just drop them into the chat box, and I think Nick's going to be watching out for them for me. Okay. Okay, Ron, to start with, could you provide an overview of what Project Loom is for everybody?
Yeah, so the goal of the project is to make it easy to write concurrent applications. What are concurrent applications? Those are applications that need to handle a great many requests, or a great many tasks that are largely independent and compete for resources. So the canonical example, and one of the perhaps primary uses of Java today, is for writing servers. If you have a server, you are serving requests from many users. Those requests are largely independent, but they all compete for your resources. And the goal of the team that maintains and writes a server is to handle as many requests per unit of time on given hardware. And the goal of Project Loom is to make that much easier.
Okay, great. How did you become involved in Project Loom? How did you get involved in the overall project?
So several years ago, I was working at another company, and we had an in-memory database that was designed for highly concurrent use. It was extremely performant. And in order to make efficient use of it, you had to use asynchronous programming, like use it with callbacks, etc. And when we came to prospective customers, they said that under no circumstance will they ever write in the asynchronous style programming. And so I looked for solutions, and I liked the general approach that I'd seen in Erlang and in Go of having user mode threads. So those are threads that are implemented in the runtime, and I wanted to see if it's possible to do that in Java. And I found some library that does like the first hard part. I took it, I forked it, and I added the other missing pieces, and that became a library called Quasar. So it started pretty much as a side project meant to help to use our database. But it sort of took off on its own, and I was invited to give a talk about it at the JVMLS, so the JVM Language Summit that takes place on non-pandemic years in the Oracle campus in Santa Clara. And after I'd done that, so maybe a year later, Brian Getz asked me if I wanted to join the team and do similar kind of work in OpenJDK. And after I was no longer working for that company, I said, sure, okay, and I came aboard.
Okay, great. You mentioned the user mode threads. What do you mean by user mode threads? What's the premise of them?
So in Java, we have, the Java standard dictates that Java offers threads, which are these small processes that share memory address, and they can run concurrently using some unspecified scheduling mechanism. While the Java standard doesn't dictate how those threads should be implemented, OpenJDK, which is the primary implementation of Java, has been for the last 25 years, implements today's Java threads as just thin wrappers around OS threads.
Okay.
So when you create a Java thread, in fact, when you start a Java thread, there is an OS thread that's created. And that is where we run into problems, which I'm sure we'll talk about more later, but the operating system can have only so many threads. And in fact, the number of threads that the number of active threads and that a modern OS can reasonably support is only, I don't know, a few thousand, something like that.
Okay.
It is orders of magnitude below the number of, say, open socket channels, open sockets that it can support, which can be more than 1 million. So if you want to write your code in a manner that assigns a thread for each open connection, you'll find that you're off by orders of magnitude. And that is one of the things that makes writing high throughput concurrent applications hard. So, but threads don't have to be implemented in the operating system in kernel mode. They could be implemented in user mode by user processes. And if you're writing in Java, the user process is the Java runtime instance. And we could implement threads in the Java runtime rather than use the ones provided by the OS and do that much more. So that is what user mode threads are. And the reason why we want them is that the Java runtime knows much more about Java programs than the OS ever can. And it can implement those threads much more effectively and give you a much greater number than the OS could.
Okay, just to expand a bit there, I'm assuming, given my limited knowledge about the topic, that there is some management going on between user mode threads and those OS level threads in Project Loom. Is that something that Project Loom's covering, or
when you
mapping the virtual threads over to the OS?
So the goal, when you have threads, you have something called a scheduler, and that is responsible for assigning the code that's running in the thread when it is ready to some CPU call. Of course, the kernel has direct access to CPU calls, but user mode programs like the Java runtime do not. So instead, we approximate CPU calls by having a small number of OS threads. We call them platform threads, and we schedule the our user mode threads on top of those, as if so those small number of OS threads represents OS calls for us, CPU calls for us, and the scheduler assigns the great many virtual threads, could be millions, onto that small set.
Okay, you touched on it earlier. From a Java language or the JVM perspective, what's the problem it's aiming to solve for Java developers?
So today, Java developers have writing concurrent applications are faced with a dilemma. They could write code in a very straightforward manner, the kind that they've been taught since Java 1.0 days, whereby they, whenever and you know, the servlet model is entirely built around that, where when there is some incoming request and you start a transaction, that transaction executes start to finish on some thread. It might offload some work to other threads, but the thing is that it holds on to at least one thread from the time it starts until the time it ends. And that means that at any one time, the number of threads you will need to hang on to is the same as the number of concurrent requests. But that number, if those threads are OS threads, you are limited to only a few thousand. And for some applications, that's not enough. By the way, the number that's required is easily computable by the rate of arrival and the average duration of each transaction. If you know the rate of requests you're getting from users and how long on average each of them takes, you can calculate how many concurrent requests you need to manage. And if you write in that style, this is the number of threads you'll need. And that could be more than the OS can provide. So, but that code is very straightforward. And the entire platform is built around that. It's not just the language. You asked about language. It's not just the language. For example, when we have, I don't know, a for loop, you know, changes the program counter on a certain thread. It's not just the language. The Java platform has troubleshooting context, right? So if you have an exception, it helps you. It attaches some context to the exception that would help you troubleshoot it. What is that context? It is a stack trace of the thread where the exception occurred. So it's also built, it assumes that a thread is what gives you context. When you use a debugger, you step through instructions. When you step over or step through instructions one at a time, what is it that you're stepping through? You're stepping through the execution of a particular thread. When you're using a profiler, the profiler arranges and groups what your program does by thread. So the entire design of the Java platform is built around the assumption that a context of something you want to do is attached to a thread. But that gives you some scalability limitations, as I said. So the people who use that style will find that they may not be able to make good use of their hardware resources. And what they'll need to do is that they'll need to buy or rent, you know, many more servers, even though they're not using each of their servers to its full capacity. So the server will be underloaded, but they still need many more. So they'll be wasting money on hardware. What other people do, they say, okay, that limitation is caused by that model of handling a transaction start to finish on a thread. So let's not do that. And let's say that if in the course of processing a transaction, we need to make a call to some other microservice or to a database, while we are waiting for the result to come back, let's not block the thread. Let's not hold on to that precious thread that we have so few of while we're waiting. Let's return it to the pool, let other transactions use it. And when the IO operation has finished, it will reschedule us and will continue. And that is called the asynchronous style. And there are various frameworks that try to make writing code in that way easier. But it requires using a completely different set of APIs. But worse than that, it loses. I say that it's disharmonious with the platform, because when you get an exception, it would still give you the thread context. But now that thread is shared by many interleaved transactions, and you don't know which transaction you're part of. You can't step through this kind of code in the debugger. It jumps through the scheduler from one transaction to another. You can't see that how each transaction is handled, and you can't profile it, because if you return the thread to the pool every time you wait for some IO operation, if you use JFR, which is the current profiling mechanism, or built-in profiling substrate in the VM, it doesn't know that there is some non-blocking IO operation going on. All you see in the profiler is that you have idle thread pools, and you won't know that your system is actually under heavy load because it's currently running some expensive IO operations. So those people would be making very good use of the hardware, and they won't be unnecessarily spending money on hardware, but they will be spending much more time on developing their software, much more effort, and maintaining it, debugging it, troubleshooting it, etc. So they need to choose between wasting money on hardware and wasting money on development. And if you reduce, and all that is caused by the underlying problem that a thread is an OS thread, and we can't have as many threads as transactions. And what Loom does, it says you can now have as many threads as you like. So you write simple code, you write code that's harmonious with the design platform. You write code that is very similar to the code you already write. In fact, Loom barely changes, it doesn't change the language at all. And it barely adds new APIs. And all of that without, while making good use of it.
Okay. You touched on earlier that you've made few changes to the Java API, but you said that there was changes to the Java platform. What aspects of, to the JVM platform, what aspects has Project Loom required to have changed in the Java or the JVM platform?
Wow. First of all, you're correct. The first time it's a Java platform, not the JVM platform.
Okay.
The JVM is just a relatively small part of it. So when people say JVM, they normally mean Java platform, except maybe the language, which is just a small portion of it. So we had to, what didn't we have to change? Well, not the language, but everything else. Everywhere where in the JDK code, where there is some operation that might block a thread, namely IO, or some synchronization on the classes in Java util concurrent. So in all those places where we need to block a thread, it now transparently asks, is the current thread a kernel thread or a user mode thread? By the way, we've decided, well, we call our user mode threads virtual threads. So I'm going to use that name. And if the current thread is a virtual thread, then it doesn't block the underlying kernel thread. So we had to make extensive changes to the standard libraries, standard JDK libraries, but without changing any of the APIs, right? So if you have, I don't know, the socket read operation, you will continue calling it as you do today, and it will continue behaving as it does today. But under the covers, it asks, are you on a virtual thread or an old platform thread? And if it's an old platform thread, it will block the OS thread as it does today with some syscall. But if it is a virtual thread, it will not. It will do the internal thing in the runtime. Now, so that's in the libraries. Also in the libraries, we've implemented those virtual threads themselves, right? So how they're assigned to their worker threads. So the scheduling mechanism to assign them to worker threads, that's also in the libraries. A part of that is in the VM, a very small but important part is in the VM. And that component is called a continuation. So a thread is made of two capabilities, not just in Java, a thread in general. So a thread requires the ability to suspend itself, to say, I'm running some code in a loop, and then at some point, I have no other computation to do. I want to wait for something. So it needs the ability to suspend itself, preserving its state, and later on, for something to say, okay, now you can continue. That mechanism of suspending and resuming some computation while preserving its state is called the continuation. That the mechanism that decides when to run you, that is called the scheduler. So a thread is made of a continuation and a scheduler. The scheduler we've implemented in the libraries. The continuation is implemented in the JDK. In the VM. There is no actual concurrency there. It's just a runnable that can say, I'd like to suspend myself. And the next time you run it, I will continue. That's the only thing that's on the VM. But doing that was a big challenge. And in fact, I think we rewrote everything pretty much from scratch twice, if not 3 times. The challenge there is that the operation of suspending and resuming must be very fast, because it might need to be done, millions of times a second. And some of the interesting challenges there. So implementing that is very, very different between different languages and different runtime. Doing something like that in C will have completely different requirements and characteristics from doing that in Java. So it's very important when people hear, about some other language, this was hard for us, this was easy for us. None of that carries over to different languages, because different languages have different constraints and different abilities. So one of the things that characterize Java is that we have very good garbage collectors. And in this case, it's mostly a blessing, but also a bit of a challenge. It's a blessing because implementing those continuations might require allocating memory very efficiently and at more or less arbitrary points. That is something that languages that don't have garbage collectors find very hard. So their memory allocation is not as efficient, and they need to be careful about where they do it so that they can clean it up later. On the other hand, the interaction with a garbage collector is not trivial. The garbage collector needs to find, in all of our Java objects, it needs to find where our pointers are. So in Java, we have references to other objects, and the garbage collector from time to time needs to walk our objects and to say, okay, so I know where the references are, and traverse them like a graph. That is pretty straightforward for the ordinary Java objects we have today, where they, so today, they're either arrays or user-defined classes. So, and in both cases, you know exactly where those references are, and their position can't change. If you write your own class, you have your fields, some of them are primitives, some of them are references, and that always stays the same. Same goes for arrays, right? So an array of int would never contain any references, but an array of string could contain references in all of its cells. With continuations, it's different, because continuations need to are objects that contain a stack. And if you think about it, today you do have references on the stack, all of your locals. So if you can have init local and you can have a string local. Your string local contains a reference, but you can call a method that has a string local, and then that method returns. It pops off the stack, and then you call another method, and that method has different locals. So where your string reference used to be, there's now an int. So the layout of where the references are changes. So finding where the references are is a challenge, and we need to do it not just for thousands of stacks, but potentially millions. And that was a very interesting challenge. It took us maybe a year and a half to come up with a new solution to how to do it. Finally, one of the biggest challenges has actually been to how to. So I mentioned before that it's not just about the Java platform is not just about writing code, but also about profiling it and debugging it, etc. And we want to give people the same experience, or something very similar to what they have today with threads, with those new virtual threads. And much of the work has been, and that is still ongoing, has been supporting debuggers. So debuggers would need to step through those new virtual threads transparently, just as they do with today threads. And recently we showed a demo of it's working to one of the Java architects, I think it was Brian Getz, and he said like, and as sort of a joke, but he said, well, that's how it's always worked. What took you so long, right? So that's what people say, that in terms of API surface area, Loom changes hardly nothing. All it does is give you the ability to create millions of threads. And the challenge is to give the illusion that everything else stays the same. The debuggers will continue working as before, but under the covers, there are completely new mechanisms. Today, they go through the OS, and now they go through the Java runtime. So I'd say that supporting debuggers has also been one of the greatest challenges.
Okay. Sounds like quite a challenge. The schedule is something might come back to later. So what is the current status of Project Loom from your perspective? I don't want to ask when's it going to be complete, but where are you in the what's the project process that the team is going through?
Yeah, I hope we're in the home stretch. The implementation on the VM is largely finished. We still have some corner cases, and we are currently in the process of completing an ARM64 port. So all that work, much of it is written in machine code or assembly, and that is CPU specific. So currently we only support x86, and these days we're working on supporting ARM64 as well. So that's as far as the VM goes. In the libraries, most of the things have been completed, but I mentioned that the API surface areas changes are very small. We basically added a few methods, but we're not fully happy with them yet. So it's just tweaks to the API. It's not as simple as it sounds, because what we do has to stay there, for the next few decades. And it's not just about giving users something that works, but also giving users something that would be easy for them to discover and hard for them to get wrong. So even though there are only a few methods, we want to make sure that pedagogically they're presented correctly. So some of the discussions we're having now is exactly, so we have some a number of static methods in which class to put them. If we put them in the class we have them now, we think that people, again, pedagogically would associate those methods with the other existing methods. So this is a point where, this is a bike shedding point. So there comes a time when you have to argue about the color of the bike shed, and this is it. So I hope that means we're in the home stretch. As for the debugger support, we still have some bugs over there that we need to fix. But yeah, I'd say largely it's about bug fixing, completing the port to ARM64, and polishing the API.
Okay. Just to rewind maybe a bit, what you mentioned earlier in your previous project Quasar, that you'd looked at Erlang and Go. What were the reference points or inspirations or drivers for Project Loom? Was there elsewhere that we? Sorry,
Erlang and Go. Yeah.
Okay, those were the two.
Yes. We didn't do so. Someone in the chat mentioned previous attempts to do threads that are more lightweight than today's kernel threads in various places. And whenever it's been attempted, either in Solaris or in Windows had something called fibers in the, maybe I think they still do. Whenever that's been tried at the OS level, that wasn't a good success. And there's a reason for that. And the reason is, well, I won't go into too much detail unless you want me to, but in short, the most important factor is the number of threads you can support. And the most expensive part of the thread is the memory required to hold the stack. And the OS cannot know how different languages use the stack. It normally has the option, so it just gives you today a fixed size stack. So it has to be large. And the only place where you can know where and how a language uses a stack and where it's okay to grow it and shrink it is in the language runtime. And we've seen that where this mechanism was successfully used, that was not in the OS, but in some language runtimes, specifically Erlang and Go. And where it has been used in this way, it's been a great success. And Go programmers love it, and Erlang programmers love it. That's not to say that we've adopted everything else other than just having many threads. So, for example, Erlang doesn't have by default a shared memory address. It just uses message passing, and of course you could do that without a thread, but that's not part of Project Loom. We're not telling you must use message passing. You can if you want. And Go has some features where, I don't know, it only uses channels, and you can't have a reference directly to a Go routine, which is their own kind of thread. And you can't, the way you can interact with it is limited. So people suffer from problems where they just have, Go routines running in the background and they don't know, and they're left running forever. So that doesn't mean that we've adopted every aspect of the implementation of those two languages, but certainly it showed us that it can be done very effectively if it's done in the language runtime. Other languages have gone in other directions, where they do something at the language level called syntactic routines or async await. That is much easier to implement, but it doesn't nearly solve all the things we wanted to solve. You would have to introduce new concepts both to developers and to debuggers and profilers to work with those, and it splits the world into the thread world and the coroutine world with no benefit. But the reason some languages do it is that in some cases they have to. Either they don't have a GC and this gives them some benefit, or they don't have access to in order to implement user mode threads efficiently, you need to have access to the compiler backend. Like I said, some of the work we did was in machine code. If you're only operating at the Java bytecode level, like I did in Quasar, for example, you're very limited in what you can do. So languages that can't change anything below bytecode, namely the VM, are limited just to that model. And we saw that we could do it on the one hand, and the extra effort is worth it because in the end, the experience users have is much better in all respects.
Okay, great. I've just got one more question before we open it up to the audience. I think we've got some questions that have come in. You mentioned earlier scheduler, and I noticed that's something Project Loom, there was talk about bespoke schedulers. Is that still something that the project wants to?
That's a good question. The answer is yes, but it might not be in the first preview. Okay. That is one of the API aspects for the simple reason that we haven't had time to discuss that particular API enough. The amount of time it takes to discuss each and every method, people wouldn't believe. It could take months, right? So we didn't have time to talk about that as much as we'd like to. And we don't want to put anything out there that hasn't been fully fleshed out. And we wouldn't want to delay the release of what we have aside from that until we like what we have. But yes, that is something that we want to have, but it might need to wait for second preview, etc.
Okay. I think that was all the questions that we prepared.
Yeah, right, cheers. So yeah, I've got a few audience questions. I think you've already touched on George's question around Solaris. He was kind of trying to highlight a little bit around like the scheduling and priority of threads and some of the ways that early Java got around that.
Yeah, so first of all, the implementation of green threads early on, and the reason it was abandoned, part of it was technical, but not exactly for the and I didn't know the full history. But on OSs other than Solaris, at least, green threads were just single threaded. They couldn't employ any processor level parallelism. So the virtual threads we have now are quite different in that regard. The problem with, I don't know what the exact issues were with Solaris lightweight processors, but virtual threads are very different. They're implemented entirely in user mode. And when it comes to priorities, well, that's a whole other question. So the default virtual thread scheduler does not support priorities, but most operating systems don't either. Years ago, maybe a couple of decades ago, when I learned about and I did some hard real-time work. When it comes to priorities, there are basically two options: do it efficiently and do it correctly. Choose one. Real-time operating systems support thread priorities very well, but their scheduling is very inefficient, and that's okay because when it comes to hard real-time, it's okay. You don't care about performance. You care about hard deadlines. So you don't care if your deadline is, I don't know, 1 millisecond. You don't care if an operation takes 500 microseconds if it could have taken 2 nanos, as long as you meet the deadline. So real-time schedulers that do priorities well are very inefficient, and they're not appropriate for use cases outside real-time where performance matters. On the other hand, implementations in ordinary operating systems, they don't really do priorities that well. If you tried it, it sort of works, but it doesn't correctly preempt a thread with a lower priority and takes care of something called priority inversion. It's something every real-time operating system needs to handle. So the worst thing that can happen is that if, say, a low priority thread holds onto a lock, and now a new higher priority thread comes along and it wants to obtain that lock, and the scheduler wants to schedule the high priority thread, but it can't progress until the low priority thread runs and releases the lock. So in that case, the scheduler needs to schedule the low priority over the high priority, and that's called priority inheritance. And that's very hard to do correctly, and most operating systems don't do it. So the default scheduler does not support priorities at all. If you like, what you could do is, and if you like the priorities your operating system gives you, you can just have multiple schedulers, each of them using platform thread workers so that the workers have the OS priorities that you like, or what John mentioned before, you could write your own scheduler when that's supported to implement priorities. But again, I think you will still find that that trade-off between doing it correctly and doing it efficiently. Yeah. That's
useful. Yes, we've got another question from Simon. So, are there any types of application that could be implemented with asynchronous programming but couldn't be implemented with virtual threads in a straightforward style?
I can't think of any, but it's like, and the reason that is that you can think that what everything compiles, it compiles the same thing, right? So when you write a code using virtual threads, it essentially compiles and emits the same instructions to the CPU that would have been emitted if you were writing your asynchronous style. So it's like different languages. It's sort of like asking, are there any programs written in Java that could be written in Scheme and vice versa? Yeah, so, there could be some ergonomic differences, but they compile to the same thing. So it's just a matter of how you express the algorithm. The algorithm underneath it covers the same. So I don't think there are any. It could be that in some highly unique cases, you'll find that one or the other might have lower overhead. You should notice it in 99.99% of cases. But there are cases where using callbacks might have less overhead than using virtual threads, and there are cases where using virtual threads would have less overhead than using callbacks. The reason is that virtual threads need to do a bit of work, like I said, in the garbage collector to maintain those continuation objects on the one hand, but on the other hand, they reuse the same memory, same as a stack does. While if you use callbacks, you have to allocate memories again and again. So there are cases where one or the other could have slightly different performance, and it's not that one of them will always be better, but ideally that should happen only in a minuscule and negligible a portion of cases.
Yeah, that makes sense. Makes sense. So I've got a question from James Shaw. So tail calls are mentioned on the Project Loom website. What motivated tail call elimination, and what's the vision for tail calls in Project Loom?
Ooh, I don't want to talk about it too much because tail calls, tail call elimination or tail call optimization is a big subject in itself, and it's part of the purview of Project Loom, but we haven't started working on it simply because we had to start somewhere, and that was virtual threads.
Right.
Tail call elimination is very important for many things, and that's why we want to do it. There is a talk by Guy Steele about it. I don't remember the name, but perhaps if you Google Guy Steele and tail call, you might find it. So I suggest you do.
Fair enough. Well, so I've got a question here. So with Project Loom, do we have control which thread model to use during runtime, virtual or OS level?
Yes, absolutely. And you do that on a per thread. Each and every thread you create, you can choose whether you want it to be a platform thread or a virtual thread. And if a virtual thread, you can choose which scheduler you want to use it. Of course, most of the time you don't like today, you don't write code that creates them one by one. You create some thread factory, you pass it to some executor, and that tells the executor what kind of threads to create for you, and that will stay the same. And yes, and that way you could even indirectly tell the executor, instead of creating platform threads, create virtual threads, or another executor to say that one I do want virtual threads. But if I'm one thing that's very important to mention, since I'm using the word executor, you should never ever cool virtual threads. If you find yourself cooling virtual threads, you've done something wrong. That's not to say that you can't use executor services. It's just that you should use executor services that create a new thread. And that's one of the small things we've added to the API, executor services that create a new thread for each submitted task rather than reuse a pool of threads for different tasks. You never want to reuse threads for multiple tasks with virtual threads.
So the idea there is that they're cheap to create and, clean up afterwards, and there's no benefit essentially of using pools.
Right. Not just that, there is no benefit and there is some harm.
Right. Okay.
You want to keep tasks to threads, the relation between them to be one-to-one. That makes everything easier.
Yeah.
Also, I should say that never mind, I forgot all of it.
The thing that kind of comes to mind, like for me with that one, I've never gone this low level, but you always hear about thread locals and the management of state across threads and stuff like that. So I suppose by not having a pool, you remove that complexity.
Right, but I remember what I want to say, and that is, some people think that if you want to use Loom in your application, you would replace your existing platform threads with virtual threads. That is not what you want to do, because remember, the advantage of virtual thread is a number. So having 10 platform threads versus having 10 virtual threads will give you exactly the same result. What you want to do is to have a new thread. You want to have many more threads. So you want to have a thread per task. So you want to give each of your tasks a new thread. That doesn't mean you have to completely rewrite your application, quite the opposite. Today, normally what we do is we take a task, we submit it to an executor that has a pool of threads. What you need to do is just change that executor instance or executor service instance so that it creates a new thread for every task. So it could be quite a small change.
So
but tasks become threads, not old threads become new threads.
Yeah, so taking like a practical example then, like with I suppose a web server, which I might have like a HTTP kind of connection tool, which is that kind of a typical example where you've got a thread connection and
exactly. So that's where you start. So today, if you have some I don't know, use Jetty or something, it has a thread that accepts connection, and then if you're using the thread per request model, it says for every connection, it starts, I don't know, a servlet as a task and submits it to some executor, which is a cached thread pool executor.
Yeah.
Just replace that with a new virtual thread executor that would create a new virtual thread for each task.
Right. Cool. Makes sense. So I've got another question from George. So what is your view on what seems to be the emerging topic of structured concurrency as a way of simplifying concurrent apps?
I absolutely love it. It was, I think I was first introduced to it. I missed the Martin Sustrick blog post, but I was first introduced to the idea when I read Nathaniel J. Smither's blog post about Python, I think. And that was one of the very few times in my career when I read a blog post by someone I hadn't known before and was immediately convinced that this is absolutely the right way to do things. So I was an immediate convert, and we've decided that we want to have structured concurrency in Java, and that is the right way to program. But structured concurrency is still rather new. And there is no, so, well, everyone agrees on the same idea. So maybe to those of you who don't know what it is, it's very saying a few words. The general idea is that when you start a thread, it's not fire and forget. If a thread spawns another thread, it waits for the child to terminate. Or a thread can't outlive its parent. And in fact, good structured concurrency takes us further, where normally you don't want even a method to spawn a new thread and return and leave it running without anyone looking at it. Every thread has some supervisor, and that is similar to supervisors in Erlang, but I think even nicer than that, that waits for it. And because virtual threads are so cheap, it's okay to waste another thread that just does nothing but wait for multiple others. So that is structured concurrency. And while everyone agrees, everyone likes the idea, there isn't yet a consensus for exactly how to do it, and every language does it differently. So suppose, just to give an example of what questions aren't universally solved, in structured concurrency, it's very common for a thread to say to spawn a group, a set of some child threads, say each of them is going to perform an HTTP call to some microservice, and then it waits for all of them and collates the results. And you want that if the parent thread is cancelled, then all the child threads would be cancelled as well. But what should you do if one of the child threads throws an exception? Is that propagated to the parent thread, and then the parent thread would, by default, cancel all the other children? So that means if one sibling dies, they'll also kill all of its other siblings or not. And different languages have different decisions there. And we didn't want to commit to anything for the next, decades. And those things, unless there's a clear consensus. So in fact, we normally try to be like the last mover, see what everyone else has done, see what works best, and adopt that. So what we're going to do is at first have something very minimal. So mechanisms, and some of them already exist in Java today. So if you look at the executor service API, we have, a wait for termination. We have invoke all, invoke any. We have methods that allow you to say, I want to do a few tasks and wait for the first, and then cancel the rest. I want to wait for all of them. So some parts of structured concurrency have already been in Java. Something that wasn't true for Go, and that is why structured concurrency in Go is harder to fit in. In Java, it's quite easy, but we didn't want to commit to any of these cancellation protocols. So what we're going to do is something rather simple, something that is largely based on APIs that people already know, like execute a service. But when I mentioned at the beginning, where do we want to, when I mentioned when we're arguing about where to put those methods, I was talking exactly about that. So the problem with execute service is, even though it fully supports structured use, that is not the way people are used to thinking about it. People think of an execute service as something that is an interface to something that's very big and heavy and very long-lived. And even though it's not specified in the interface, no one today would create an execute service and destroy it, a million times a second inside a single method. Even though there's no, philosophical reason not to, just that connotationally it's become associated with very big thread pools. So even though this kind of new structured executor service is still an executor service, we're debating how to move it away from the executors class along with all the other executor service, so that people know, at least, or give it a different name, so that people know not to think about it in the same way they've been thinking about executor services today.
So these are the real challenges with the API and thinking about what's going to make sense for developers ultimately, isn't it?
Right. And that precisely is one of the things that is currently under discussion. One of the things we still need to polish, where to put those structured concurrency methods.
Yeah, that sounds good. Let's check. I think we've covered all the questions. There was a final one around an example, I think, that was going back to the virtual OS level threads, just talking about virtual threads or platform threads. But I think we were saying that when you talk about platform threads, you're talking about the Java kind of user mode type threads, or because as I mentioned, there are virtual threads or platform threads. I think they might mean OS threads for the platform.
Yeah, no, we call them so.
Yeah.
So the reason we call them platform threads, and that's tricky because the Java specification. So platform threads are today's threads. The Java specification does not dictate that today's thread will be implemented by the OS. So we had to come up with a name for the old thread, even though in OpenJDK it is an OS thread, so we called it platform thread. So platform threads and OS threads on.
Right. That makes sense.
I've got a few questions if you don't mind. I've waited for everyone to get their turn.
There is a question. There is a question about file processing. I'll try to address it directly. File processing is interesting because there currently does not exist most OSs don't support any kind of non-blocking API for file processing. So doing that would likely be equally bad on both. In the future, we might want to use IO Uring and Linux so that we can do that for file processing as well. So it's hard for me to answer it, to give you a definitive answer without knowing the specific use case. You'll need to profile and check. But one thing I would like to express is that it's not very important to know ahead of time whether you want virtual threads or platform threads, because switching between them is very easy. You just say, use the thread factory that gives me platform threads, or use the thread factory that gives me virtual threads. So I would say try both and use whichever one works. It's very easy to change even after the fact. It doesn't change the way you write the code. So write the code, pick one, and then use the other and see which of them works best. Yeah, correct.
Yeah, good.
Yeah. Is there a theoretical upper limit on how many virtual threads you could run? So will it get to a point where the thread schedule is just churning through virtual threads and not really getting a lot of work done?
Well, yeah, but that's not a theoretical point. That's so obviously there's a limit. At some point, your RAM will be exhausted, and the thing you're saying about the schedule is actually not as much of a problem, because it doesn't have to do with the number of virtual threads. It has to do with how frequent, how active they are. So if you have, I don't know, let's say 10 cores and 50 threads, it could be virtual, it could be not, it doesn't matter, 50 threads, all of them demanding more CPU, then you're in trouble. But if you have 10 CPU cores and 1 million threads, each of them just wanting to do a tiny bit of work once a second, then it's quite easy. So the resource limits aren't about the number, they're RAM and the CPU, and they're still there no matter what. We can't change them. We can just help users write code that is simple and at the same time manages those resources optimally. But at some point, you will exhaust one or the other.
Okay, so how does the JVM know how many OS threads it needs to allocate for work? So say for example, I spawn off, I don't know, 100,000 virtual threads. How does the JVM know that it needs to go back to the OS to say, right, I need another 4 OS threads, I need another 8?
So the resource you want to optimize is CPU cores, not threads. OS threads are sort of a mechanical limitation. So you want to use your CPU cores well, and you can't allocate more, right? So by default, we just have as many worker threads as you have CPU cores. But sometimes, and that's why the file operations are interesting. Sometimes we run into situations and Go and Erlang do the same thing, or run into the same issues, where the operating system doesn't support an I/O operation that blocks and doesn't need the CPU, but still hangs on to the thread. And some file operations are like that. So some file operations don't hang onto a CPU core, but they still hang onto a thread. And we do detect those. And in that case, we will temporarily ask the OS for more platform threads, worker threads. But other than that, there is no reason to do it. If we can use all of your cores, then that's the best we can do.
Okay, this is not so much Loom, but more around once Loom winds down, are you going to stay in this area? Are you going to pick up a project lead in a different area?
I see a question: will the virtual threads be serializable? Yeah, that is something that is very, very interesting. That has interested me from the start, and I did that in Quasar. The answer is I hope so, not at first. What this gives you the power to, so imagine this, you have some distributed database, an in-memory database running on a cluster of machines, and all the data is in memory, but it's spread across machines, and those machines also service requests. And then you have an incoming request to one of the servers and says, I don't know, I want to run this query, and please return the results. So that would need to, that would perform a blocking I/O operation against the database, and the database would be able to say, and the thread processing that transaction would block and wait, and the thread and the database processing the request would say, actually, you know what? I don't have that data in RAM on this machine, but I have it on another machine. So instead of moving the data, it would move the entire thread processing that transaction to that other machine. And when the blocking call returns, it will be running on a different machine. So that is very cool and very powerful. But of course, serialization is always a best effort kind of thing, because if that thread is serving a transaction, you can't serialize the open socket. So it would have to somehow detect this and give back the response some other way. So there are some challenges there, and those challenges will probably not be solved in the JDK, but by user code. But that is certainly a capability that I would very much love to see because it's very cool.
Okay, I think that's all we've got time for today. Thank you very much for joining us today at the Manchester Java Community, Ron, and everyone else. What's the best place for developers if they want to learn more about Project Loom to go to?
Oh, yeah. So let me find that.
And is there anything else the wider Java community can do to help Project Loom move forward?
So first of all, right. So I would say go to this site where we have the early access builds. It has a link to the mailing list. Yeah. So the best thing you can do is try Project Loom early access builds. You don't need to build the JDK itself. Download it, use it. Tell us about your positive and negative experiences. So it's best. The best feedback is one that comes out after actual use. In addition to that, I don't see. Let's see if I have the wiki with the getting started. Yeah, found it. And this has some getting started guide. As I said, the API surface area is quite small, even though it changes from time to time. So the getting started guide is quite short and it's very easy to learn pretty much everything you need to know. So there.
Wonderful.
Okay. Thank you, Ron, for joining us.
Yeah, thank you very much. Thanks for your time. It was really good. And thanks everyone for attending.
Wow.
And cheers, Jonathan, for hosting. Did a great job.
Thank you, everyone.
Yeah. See you later, everyone. Thanks. Bye.
Bye.